Okay, now our third video has to do with nonlinear or non-rectilinear relationships. And the reason why I'm making this distinction between linear and rectilinear is that the linear model just means that it's additive, and a nonlinear model means that there's not a linear or additive relationship. And that's not something that we're going to be covering in this class, and the reason for it is that nonlinear models get very complicated and the interpretation is difficult and what have you. What we're talking about here in this class is mostly the general linear model, which is regression. And the general linear model, or even the generalized linear model, which we're going to discuss in a little bit, is a model that assumes that there is some rectilinear or straight line relationship between our predictors and our dependent variable, and if it's not a straight line, we run into some interpretation problems. And the best way to demonstrate that is to just show exactly what happens. Whoops. Hold on a second, I gotta change this. Okay. Okay. The best way to show this is to show the Anscombe data set. The Anscombe data set is a fascinating one. It's one in which it has very simple characteristics, and the best way to show these characteristics is if you look at the means and standard deviations of each one. You'll see it's a data set with 4 pairs of data. Okay, pairs because it's bivariate relationships. X1 goes to Y1, X2, Y2, and so on and so forth. So if you take a look at X1 here, this is a summary in this lower panel. The minimum and maximum remains across the board for most of these of 4 and 9, but that's really not that's not the most important part of this. The most important part is the mean and the standard deviation for each one of these variables is identical. Similarly, the mean standard deviation for Y1 to Y4 is identical. What's different is, and also the regression for each one of these is identical in that the regression line, for the most part, between X1 and Y1, X2 and Y2, X3 and Y3, and X4 and Y4 are all the same straight line. And again, the best way to look at that is to look at the plot. This is what we should be doing from the beginning, and that's why I always do bivariate plots. But if you take a look at this is a normal scatter plot in the upper left-hand corner, and this is between X1 and Y1. This regression line is identical for all 4 data sets. The distribution of the data around this line is exactly what we expect from most social science data. But take a look at what happens between X2 and Y2. Well, if you look at this is clearly not a very good summary of this underlying relationship. Underlying relationship is curvilinear, not rectilinear. So it's not a straight line, and because it's not a straight line, you're going to get odd predicted values. Similarly, here, this is a situation in which you have an outlier, and the outlier influences the values. And we'll talk about this later. And similarly, this is an outlier where you have no relationship, or you should have no relationship, because X4 is invariant except for one data point. This second figure here in the upper right hand corner is what we're talking about in this little segment here. So it's a simple nonlinear or rectilinear relationship, and now I created a variable called X4 that is a nonlinear, non-rectilinear relationship with y. And you'll see here X4 I created by squaring the values of y. By squaring the values of y and then adding some error, what I've done is I've created a curvilinear relationship between X4 and y. So if you want to take a look at this, what I'm going to do is I'm going to run 2 separate models. And the reason why I'm running 2 separate models is I need to be able to demonstrate that there are, I probably should square this instead. That way we don't run into problems with square roots of negatives. Okay. Okay. Simple fix. So now I have two models, and what I want to show you is what those models look like when I plot them side by side. So these are the raw values, and this is what happens when I plot the raw values between x4 and y. And what happens is I have a negative relationship, and the reason for that negative relationship is there is a curvilinear relationship between x4 and y. If I square y, and I have an x4 as a non-transformed, oops, and I should change this because this is inaccurate. I've transformed y. So let me run this over again. No. Yep. If you look at this, now I have a much better characterization of my data values because I've taken into consideration what the relationship is between x4 and y. And once I transform one of the variables, and we'll talk about this later in the semester about the bulging rule and different ways of anticipating and correcting data or transforming data based upon the observed distributions, that if you correct the data, you'll actually have interpretable regression coefficients. So these nonlinear relationships that we create or that we observe by having underlying curvilinear relationships or complex relationships among our predictors and our dependent variable, they need to be diagnosed before we run our regressions. And our regression models will definitely run and we'll get results. The problem is we may interpret them incorrectly because the regression parameters are based upon a rectilinear relationship, and if you have a non-rectilinear relationship, you interpret it as such, you're going to have regression parameters that are not really helpful in predicting future events. Incidentally, I created a little function here so that you can run regression diagnostics, and these are regression diagnostics. Whoops, I don't know what happened here. Looks like I need a parenthesis someplace. Okay. Everything runs. Okay. These regression diagnostics help us determine whether the assumptions in regression were met. And starting next week, or maybe the following week, we're going to go through all of the regression diagnostic, the assumptions, and then how these diagnostics really help you out. So this function will help us plot out all of the regression diagnostic plots. You can see them in one window, and you can look quickly at what's happening. And so after this, we're going to cover a few more sections: categorical predictors, nested data, and nonlinear interaction effects and analysis of discrete variables. So stay tuned for the next bit.